into chapter 3, where you'll remember that we're in the midst of two chapters that are described by the word kinematics. Kinematics means if something is moving in a certain way, we want to be able to describe it. And the way we described it in chapter 2 was if something is moving in just one dimension along a line, say the x-axis, then we could describe it using position, velocity, and acceleration. Now in chapter 3, we want to generalize those ideas of what is position, velocity. Well, we know what position means in 2D and 3D, but what does velocity and acceleration mean? How do we describe them mathematically? And that's going to take a little we have to take a little side road into reminding ourselves about properties of right triangles and learning about the idea of vectors. So what we're going to do in this chapter is first describe some properties of right triangles that you learned about probably in high school, and then use those properties to help us understand the properties of scalars and vectors. And some of you may never have heard of vectors and scalars before, but we'll define them. They're not too complicated, but they're the language in which we're going to describe position, velocity, and acceleration in multiple dimensions. So the main part of it, or we get back to physics in what I call part 3 of the discussion, where we talk about acceleration, velocity, and generalize our kinematics equations to multiple dimensions in the case where acceleration is constant. So let's go on and start with the properties of right triangles. Just a little reminder of some things that you've seen before, and for some of you it may be a little bit rusty, but we need to practice with it to get it back up front. If we want to describe the location of a point that I'm just showing here by a black dot in some xy axes, we've already defined what the x and y axes are. One way to do that is to just give the xy coordinates. That's the Cartesian way of doing things. And the meaning of those xy coordinates are, I could draw in this little right triangle here, and the meaning of that x is, what is this distance here? Of course, it would be a negative if that point were somewhat, over here or down here. But it's related to the length of this side of the right triangle, and y would be the length of this side of the right triangle. But a perfectly good alternative way of specifying where this is, if we knew where the axes were, again, is to instead specify the angle at which the hypotenuse of this right triangle is up from the horizontal direction. So we're going to think of this as a positive angle up here. Negative angles are going down in this direction from the horizontal direction, which is parallel to the x-axis for us. If you know that angle, you know that your point is somewhere on this line, and then if you also give the distance r from the origin to the point, you've uniquely specified what that point is. So we could either describe that point using Cartesian coordinates, x, y, or what is sometimes called polar coordinates, r and theta. And we want to be able to go back and forth between those two, because sometimes you know the information in one description and you really prefer to have it the other way. So let's first talk about, if you know what x and y are, how do you determine what r is in terms of x and y? And the answer is easy. If you remember one of the big facts about right triangles from high school, or maybe even before that, is the Pythagorean theorem. R squared equals x squared plus y squared, because this is a right triangle, and therefore r is the square root of x squared plus y squared. So if you know x and y, you can easily compute r. How about theta? Well, theta is a little bit more complicated, and it relies on some understanding of trigonometry, which again may not be so fresh for some of you if you haven't looked at it in a couple of years, but let's remind ourselves what it means. The relationship cosine theta is equal to x over r. At least in the United States, that we remember these things by the acronym SOHCAHTOA, which doesn't spell out any particular word, but it's supposed to remind us of some facts about the relationship between angles and the sides of a right triangle, the two perpendicular sides and then the hypotenuse. So SO stands for sine is opposite over hypotenuse. That's the SOH that I've capitalized there. Ka reminds us that cosine is adjacent over hypotenuse, And TOA reminds us that tangent is opposite over adjacent. And it's kind of a ridiculous word, but it's so ridiculous that it sticks for almost everyone, and they can remember this. So here we're using the ca part. Cosine of this angle right here is adjacent, that's the A. Cosine of this angle is adjacent. Now adjacent always means the adjacent side that's not the hypotenuse. So that's x. Cosine theta is adjacent x over hypotenuse, and hypotenuse is r. So cosine theta is x over r. And once I know that, I can easily solve for theta by applying the inverse cosine to both sides of this, and therefore now I've done what I finally asked for up here. I want to express theta in terms of x and y. I've expressed it in terms of x and r, but r can be written in terms of x and y. We could have put a square root of x squared plus y squared there. So this tells me if I know x and y, I can certainly calculate what theta is once I've gotten r. There are other ways to do it, and the second way comes from the SOH, S-O-H. Sine is opposite over hypotenuse. So for this angle over here, opposite means the side opposite the angle that we're using, and hypotenuse is r, so sine of theta is y over r. That means taking the inverse sine of both sides. Theta is the inverse sine of y over r. And finally, using the TOA, tangent of this angle is opposite y over adjacent x. Tangent theta is y over x. Applying the inverse tangent to both sides to get rid of, when we apply inverse function, we think, what? I wish I want to solve for theta. What's happening to theta? Tangent's happening to theta. How do I undo tangent? By applying the inverse tangent to both sides. So when you apply the inverse tangent, it undoes the tangent and just leaves a theta on the left-hand side. But if I apply it to the left-hand side, I've also got to apply it to the right-hand side. So theta is the inverse tangent of y over x. 3 different ways to get theta if you know y and x. So that's going one way. So what we found is that if you know x and y, you can find r and theta. We'll also see if we inspect these relationships up here carefully, if we know r and theta, we can find x and y. For example, if I know r and theta, I could just multiply both sides by r and find that x is r cosine theta. So if I know r and theta, then that tells me how to get x. This relationship here tells me how to get y. Y is r times the sine of theta. So if I know r and theta, I know how to find x and y. The problem with this discussion, or this way of viewing things, is that most people's understanding of these relationships is really tied to this picture of a right triangle sitting in the xy axes. So we're going to find that in our problems that we encounter in Physics 110, you're going to find right triangles that are in all sorts of crazy orientations. So I'm just going to draw one right here. Here's a right triangle in no particular special orientation. And you're going to imagine that maybe I know this angle theta, and I know this hypotenuse r, and I would like to know what the length of side A is in terms of r and theta. So if I know what r is, maybe r is 4 meters, and theta is, 60 degrees or something like that. How do I find out what A is? Now, most people, their first reaction is to go to the SOH-TOA relationships, and that's one way to do it. I could say cosine of theta is adjacent over hypotenuse, so therefore cosine of theta is A over r, and then I want to solve for A, so that means A is equal to r times the cosine of theta. And that's a perfectly good way to do things. The problem for me is that it requires too much mental gymnastics to do all that. Every time you want to find out what this side is, if I know these two items, r and theta, I have to go through this thing and solve for one of the variables. So I'm going to tell you something that's probably equally or more ridiculous way of remembering the SOH-TOA kind of relationships, but in a way that allows us to instantly just know the answer for this side in terms of the hypotenuse and some random angle theta. And that is, and I admit this is fully embarrassing. I wouldn't say it out loud, but for some reason this is just what I came up with when I was learning this stuff. And that is, when I start with the hypotenuse, so I imagine this hypotenuse, and I say, to get from that hypotenuse to this side or this side, I could do two things. If I want to get from the hypotenuse to this side, I sort of swing through the angle theta that I know. And I really like swinging through that angle theta because it's labeled there, right? It's the angle that I know, so I'm pivoting right through that angle. I like pivoting through the angle, and for some illogical reason, I like the cosine better than the sine, because when you learn about, the cosine and the sine in this original formulation, the cosine was associated with x and the sine was associated with y. So for a lot of people, cosine seems to come before sine. And therefore, for some illogical reason, I like cosine better than sine because I think of it as coming first, and I prefer to pivot through the angle. So to get from the hypotenuse to this side, since I pivot through the angle, what do I do to r? I multiply by the cosine of theta. So this side is going to be r times the cosine of theta. I know, it's embarrassing, it doesn't make much sense, but I tell Physics 110 students this every semester, and I would say more than half of them end up using it and really appreciate it, because once you get that relationship embedded in your head, you can do it really quick and you don't have to solve a SOHCAHTOA kind of relationship for some other variable. And we're going to need to use this skill all the time. So it will kind of slow you down a little bit. That's not to say it's really going to hurt you in this course, but if you have to stop and use SOHCAHTOA, it does put a little roadblock in so much of what we're going to do. What if instead of wanting to know that side A, I want to know the side B over here? Well, in this case, starting with the hypotenuse, I would say, oh, well, to get from the hypotenuse over to B, I'm not pivoting through that angle. I'm sort of pivoting across the angle, and I really don't like that because it's sort of violating the angle theta that I know there. Since I don't like pivoting across the angle, I much prefer pivoting through the angle, starting with the hypotenuse. I don't like that, and I don't like the sine as much as I like cosine, for no good reason, and therefore, what do I do to r to get to this side over here? Multiply by the sine of theta. A is equal to r times the sine of theta. I know, it's a little bit cumbersome to begin with, but you'll find it's much faster than thinking in terms of SOHCAHTOA. I could have said, hey, look, sine of theta is opposite over hypotenuse, and then I could have solved for b in that relationship, but it's just an extra step that you have to do. Now, maybe I don't know this angle over here. Perhaps in a different problem, I know this angle. Let's call it Greek phi or phi. I guess it's phi, but I'm not really sure. Different people pronounce it different ways, but I'll call it phi. If I know the angle phi down here, and I know this hypotenuse r, how do I find this side? Well, let's use my crazy technique, which is to say, to get from r over to this side, I'm not pivoting through the angle phi, I'm pivoting across the angle phi. In other words, I'm sort of going over in that direction. Oops. And that means since I'm pivoting across it, I multiply r by the sine of phi to get a. A is r sine phi. Whereas if I want to get this side b over here, starting with r, I would pivot through phi. So what do I do to r to get to b? I multiply by the cosine of phi because I like the cosine better and I like pivoting through that angle. Okay, so that's just an alternative. You could have gotten all those relationships from SOHCAHTOA, but my claim is it's just going to slow you down a little bit, and we're going to be doing it so often you don't want to constantly feel like, it's sort of like you're on a beach running on the sand, and it just takes so much more effort than running on a road because everything just takes, sucks a little bit of energy out of your stride. Same way here. All right, so that was a discussion of the right triangles, and now we're going to transition. I said the second thing we were going to talk about in this chapter is scalars and vectors. What are they? Well, here's the motivation. We could describe the position of an object, or 2 dimensions and 3 dimensions, using x, y, z coordinates. We're familiar with that. The problem is, we know from our kinematics discussion, we also want to describe the velocity of an object and the acceleration of an object. Velocity means how fast and in which direction the object's moving. And the acceleration means how much and in which direction the velocity is changing. How can we do this? It's not obvious how to do that with x, y, z coordinates, but we're going to use vectors. So we can describe position, velocity, and acceleration all using vectors. And, well, so what is a vector? We're going to think of vectors in contrast to scalars. Scalar for us is just going to be another name for a real number. So it could have units with it, but if I think of a real number like, 7 seconds or 3 cubic meters, those would be examples of scalars. Even pure numbers, like just 7, could be an example of a scalar. Negative numbers, too. In contrast, a vector is something that doesn't just have a size to it, it has a magnitude and a direction, and no other properties to it. So, for example, a force is an example of a vector in physics. In fact, I think I asked for examples down here. What are some examples of vector quantities we're going to see in physics? A force is one of those. You just use your intuition. We'll talk more about forces in Chapter 4. When I push on an object, I push with a certain strength. That's the magnitude of the vector. But I also push on it in a certain direction. Pushing straight ahead is different than pushing to my left. And so a force is a vector because it specifies how strongly and in which direction I'm pushing it. And pushing in different directions means different vectors. Velocity will be another example. Velocity specifies how fast and in which direction an object is moving. And we'll find that acceleration is also a vector quantity. It specifies at what rate and in which direction the velocity is moving. So those are some examples of vector quantities that we'll use all the time. Scalar quantities are quantities that don't have a direction associated with them. They might have just a magnitude. Something like if I have an object that just has a certain temperature to the object, the temperature would be an example of a scalar quantity. There's no direction associated with the temperature. Or the volume of a certain three-dimensional object would be an example of a scalar quantity. The length along a certain direction of an object is another one. Those quantities don't have a direction associated with them, especially volume. There's no way to conceive of a direction associated with a volume. So we'll be using both of them, and we've got to learn a little bit more about vectors. It looks like my video is over. Again, I'm trying to make these a little bit shorter, so let's stop here and we'll continue the discussion with vectors when we get back.